This conference will now be recorded.
So, very good evening, students. Today, we're continuing with this chapter, communication system. Today, we'll learn what is called antenna, what is the role of antenna, and what are different types of antenna used in communication system. Then we'll learn about receiver, and at the receiver end, we have to demodulate, or we have to recover the signal which we had already modulated using carrier wave. So how is that done? We'll discuss today. So first of all, what is an antenna? An antenna is basically a small length of conductor. Small length of conductor which is used to radiate or receive electromagnetic waves. Electromagnetic wave. So it acts as a conversion device. At the transmitter end, actually antenna are used both at the transmitter end and receiver end also. Okay. What is the role of this antenna at the transmitter end? Generally, it converts high frequency current into electromagnetic wave. It means antenna. Antenna converts high frequency, I'll write in short HF, high frequency current, electric current into electromagnetic wave, EM wave. Okay. So antenna at the transmitter end converts an electrical current, high frequency electrical current into electromagnetic waves. And what is the role of antenna at the receiver end? At the receiver end, it does the opposite conversion. That means it converts EM waves into electrical signal. And is fed to the input of the receiver. input of the receiver. So these are the main uses of transmitter, both at the antenna. These are the roles of antenna. Antenna can convert the electrical current or electric signal into EM wave, and it can even receive and convert electromagnetic wave into electrical signal. Okay, now I'll erase this. So antenna actually consists of a conducting wire. Okay, so there are different types of antenna being used in various communication systems. So generally we know two types of antenna. Two types of antenna we know. So what are those? One is dipole dipole antenna. Dipole antenna. And another one is dish antenna. Dish antenna. So you can see there are many things in our day-to-day life we use, but we don't know the physics. So if you study physics, you will understand like how all those things which are used commonly almost every day in our day-to-day life, we can understand what are the working principles behind them. Okay, so similarly here in this case, see, we use this antenna but we don't know how it works. Today we'll know at least something about it, and if you go for telecommunication and all those branches, you will know in great details about these things. See, dipole antenna. Dipole word has dipole, that means there are two poles. You can look here. A dipole antenna has actually two conducting wires. Two conducting wires. Okay, two conducting wires. You can see those things, this and this. And a dipole antenna is just a piece of, actually we are seeing that it has two conducting parts. Okay, conducting, or like two parts of conductors. And what are the length of these conductors? Generally the length of these conductors will be much lesser than length of the dipoles or the conductors. Length of the conductor will be as smaller as, like actually it's much smaller than carrier wave. So you can see here the two conducting wires, like this is called rods or metal wire. This is also feeder or transmission lobes. This is actually called lobe. Okay, this is called lobe. And see, this conducting wire or metal or rods, these are of actually length of lambda by 4, and as a whole the whole length of the antenna will be lambda by 2. Okay, this is the minimum length you require. The length of the dipole antenna should be such as that its resonance with the carrier frequency happens. Okay, so how to determine the length of the antenna being used in any particular case of communication, that is being done keeping in mind about the resonance condition resonance condition of the carrier frequency with the dipole antenna. So length of dipole antenna, the length of dipole antenna would be such that should be such that it is in resonance resonance with the carrier frequency carrier frequency. Okay, so this is about where here actually see this lambda is the wavelength of the carrier wave. So WV, that means wavelength. WL I should write. Okay, let me spell it otherwise. So lambda is here wavelength of carrier wave. Carrier waves. Okay, now we'll see generally we see another type of antenna that those are called dish antenna. So here there will be an SH. I'm sorry. Dish antenna spelling is this. So dish antenna. Okay. So in the previous case, you have to know the directionality. So dipole antenna is called omnidirectional. It is used to transmit radio waves. Omnidirectional in the sense, I'll let you know what is called omnidirectional. See, suppose you have an antenna. So you have antenna. Okay, so antenna, as you know, they simply a metallic wire or metallic rod. This metallic rod or this antenna actually transmit radio wave in all directions. That's why it is called omnidirection. Omnidirectional. That means it does not prefer any direction. It prefers all the direction. Okay, this is omnidirectional, 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 omnidirectional antenna used for. So this is omnidirection in the sense each and every direction it can emit radiations. That is what it means by omnidirection. Now, this antenna, what is this antenna? So this antenna is a highly directional antenna used for transmission and reception of ultraviolet or microwave radiation or microwave range electromagnetic wave in the microwave or ultraviolet frequency range. Sorry, ultra high frequency range. Okay, so these antenna are highly directional. You can see the figure of a typical dish antenna. Generally, there will be a reflector. Reflector, this means this one. Reflector is this one, either parabolic or spherical. This is called reflector. Okay, so it can be either dish, spherical dish, or parabolic reflector also. In the receiver mode, the dish actually see the dish antenna also can be used in two modes. One is receiving mode and transmission mode. Transmission mode, transmission mode and receiving mode, both way it can be used. Dish antennas can be used as receiver or emitter also. Okay, and it can actually transmit or receive microwave. Okay, it can receive microwaves and very high frequency, ultra high frequency radiations. So it can receive or transmit ultra high frequency and microwave. Okay, microwave. What is the like activity or role of this reflector, and how does this antenna work actually? What it does is, it receives or collects electromagnetic radiations and focuses them on the dipole, which converts that electromagnetic wave into electrical signal. And then at the transmission mode, the dipole converts into electrical signal into the electromagnetic wave and direct them on the flow on the reflector, which are then transmitted as a parallel beam. You look what happens. So this antenna collects electromagnetic waves. Okay, collects the electromagnetic waves like this, then they will be focused and actually they will be converted into electrical signal. Okay, electrical signal. Then thereafter, the signals at the emitter end, basically, the dipole converts electrical signal into electromagnetic waves, and those electromagnetic waves will be actually reflected to a particular direction. Okay, that's why it is called highly directional. Okay, and the gain of a this antenna gain of a this antenna is defined as P is equal to 6 into D by lambda whole to the power 2, where D is the diameter of the boundary of the reflector and lambda is the wavelength of the electromagnetic radiation. So these antenna are used in radars, satellite communication. Okay, satellite communication and radar. Radar actually uses microwave signals. So these are the use of this antenna. This antenna can be used in satellite communication and in the radar, like in case of various aeroplane communication happens actually. Microwave signal from a satellite is received by cable operator through a dish antenna as well. Okay, now we'll go to the receiver. We'll see what is a receiver do. We'll see what is the role of a receiver and how receiver actually recovers the original message signal which was modulated by amplitude modulation. So the function of receiver is to recover the original message or the data from the modulated signal. So after modulation, the wave has to be propagated to the receiver, right? And there receiver will separate the modulating signal from the carrier wave. This is the role of the receiver. This is the process of demodulation, and the schematic representation of this you can maybe, yeah, so you can see here there will be, just a minute. So the function of a receiver to recover original signal, message signal. Okay, so the process is that at the receiver station an antenna picks up, see this is an antenna that picks up the signal. Okay, at the receiver end or receiver station there will be an antenna that will pick up the modulated wave radiated from transmitter. Okay, Then by tunable amplifier, that is called tunable amplifier. Okay, by tunable amplifier, the desired signal is selected and other unwanted signals will be rejected. Okay, and then the desired signal will be amplified by the tunable. This is called tunable amplifier. Okay, then that signal will be, see, after sorting out the message signal from the unwanted signal, tunable amplifier, what it does, it amplifies the message signal. Finally, it is fed to modulator or detector, which recovers the original signal from modulated wave. After that, there is, okay, this stage we will discuss later. So see, after amplification, it will be fed, it will be going to detector, and there in the detector, what will happen in the detector? Detector will actually recover the message signal from the modulated wave. So this will be actually detecting the message signal. Message signal detect detect the message signal, okay, from the modulated one. Okay, so what is this IF stage? This is called intermediate frequency stage. Intermediate intermediate frequency stage. Intermediate frequency stage. Okay, so this, what is happening here in this intermediate frequency stage? Actually, it is to facilitate the further processing of the carrier frequency. Let me explain what is the intermediate frequency stage. What is happening here, I'll discuss. So so first antenna will receive the signal, then there will be some sorting out, and tunable amplifier will amplify that, and further what will happen, to facilitate further processing, the carrier frequency is changed little bit. Carrier frequency will be changed. That will be actually lowered by a device called intermediate frequency stage. IF stage, this actually lowers the carrier frequency. Okay, lowers the carrier frequency by a device called intermediate frequency stage. Then the signal is fed to the modulator, which recovers the message signal from the modulated wave. And to further strengthen the detected signal, it is fed to an amplifier later also. This one. Detected signal is the original signal you wanted to have. So that signal is actually very, very weak. To strengthen it, you can amplify it. So this amplification is happening once, but this amplification just after sorting out. Then also finally once again it will be amplified before it goes to the output end. Okay, This is how actually an amplitude modulated signal is recovered. We'll see once again here how detection happens. Okay, how detection, I said detector will detect. So how this detection happens, or how demodulation happens. We'll discuss now how demodulation happens. So demodulation here, or detection, demodulation or detection. So demodulation process is exactly opposite to the modulation. Modulation, what it does, it is actually uh, it is to modulate the carrier wave or carrier frequency or carrier amplitude with the message signal. In fact, carrier wave carries the original message signal. Okay, and there will be a high frequency carrier wave which will carry the message signal. Here, in the demodulation case, the process of receiving or recovering audio signal, original audio signal from the modulated wave is known as demodulation or detection. It is a reverse process of modulation. I'll write here reverse process of modulation. Reverse process of modulation. Okay. So we know that a modulated an amplitude modulated signal contains how many? Omega c, then omega c plus m, omega c minus m. So these three types of frequencies will be available in the amplitude modulated signal. So the modulated signal pass through a rectifier which gives a series of positive half cycles of radio frequency pulses, as you can see here. So this is the amplitude modulated wave input. Then this is rectified. This is actually a rectified wave, and rectified wave will be actually without the RF component. This is the RF. These are the RF component. Okay, these are the RF component. So the RF in the sense high frequency. It is oscillating. RF means oscillating pulses. So this is the amplitude modulated wave. This will be passes through the rectifier. Gives Rectifier gives a series of positive half cycles, a series of positive half cycles of radio frequency pulses, as shown in the figure. You can see that these are the series of pulses. In this case also you can see that is the processing happening, and then envelope of this pulses is the message signal. In order to detect the message signal, the Signal is passed through an envelope detector which may consist of parallel combination of low valued capacitor and resistor. Generally, a filter circuit used to be a like combination of capacitor and inductor or capacitor resistor, okay, or inductor resistor, kind of those things. So we have understood that a modulated signal, the amplitude modulated signal, when passes through a rectifier which contains a continuous variation of uh, half cycles of the signals, okay, RF signals, we say. So the envelope of these pulses is actually the message signal. Okay, this is how. See, this is the envelope. Generally, without this RF, this will be the original signal. So this is about the demodulation and receiver part, antenna part. Now I'll just take a few numerical examples related to the amplitude modulation, and then we'll be able to apply the knowledge we have already got about this communication system. Let me just take up one example. See, a message signal of frequency 10 kilohertz. If suppose a question is given like this, a message signal of frequency 10 kilohertz and peak voltage peak voltage of 10 volt is used to modulate a carrier frequency of 1 megahertz. So as you know, carrier frequency will be always greater than the message signal frequency, and the carrier signal has peak value of 10 volt. Again, you have to determine, see, the question is determine modulation index, and then second question is side band produced. You have to determine side bands produced in amplitude modulation here. Okay, so you have to find out what is modulation index. So how do we define modulation index? Modulation index Mu is defined as amplitude of the message signal divided by amplitude of the carrier signal. So here in this case both are 10 volt. So this is the part 1 answer. So it will be 1. Now we have to find out the side bands. So how to find out side bands? See, side bands are of two types: USB, up side bands or upper side bands. Those are actually defined as frequency of the carrier plus frequency of the message signal, and LSB, that is the lower side band, it is FC minus FM. So FC is given as 1 megahertz, and message signal is given as 10 kilohertz. We will convert both of them into kilohertz, and then the kilohertz means 10 to the power 3, so here it will be 1000 kilohertz plus 10 kilohertz. So it is actually 1010 kilohertz. What will be LSB? So from here you have to just subtract. It will be 990 kilohertz. Okay, this is the lower side band. Now I'll take up another question from this uh, amplitude modulation part itself. Let me just erase this. I hope you have understood this. These are very simple. So you have to understand like how many side bands are coming, like what are the side bands, upper side bands and lower side bands, and how do the how do we write those in terms of mathematics, or yeah, so mathematical formula of them we have to remember. Now another question I'll take up: a sinusoidal carrier voltage of amplitude. I'm not writing the, okay, let me write a sinusoidal carrier voltage carrier voltage carrier voltage is amplitude modulated amplitude modulated modulated by a sinusoidal voltage of frequency voltage of frequency 10 kilohertz to a depth to a depth of 30%. Calculate the frequency of amplitude. Calculate the frequency frequency and amplitude of the two sidebands. Sidebands. If the carrier frequency is 10 megahertz and its amplitude is 40 volt. Okay, so sinusoidal carrier voltage is modulated by a sinusoidal voltage of frequency 10 kilohertz. That means, see, the original message signal is this one, 10 kilohertz frequency. That is also a sinusoidal one, and this is the carrier frequency, that is 10 megahertz, again 10 megahertz, and its amplitude is 40 volt, 40 volt, and in case of the amplitude, sorry, amplitude of the message signal is not given. So also, so from here then you have to find out what are the side bands and amplitude of the two side bands if the frequency of carrier wave is 10 megahertz and amplitude is 40 volt. That means, you have FM. FM is 10 kilohertz. That means you have 0, 1, 0.01 megahertz. And see, 30% depth is there in this case. Okay, anyway, so FC, let me write first. FC is 10 megahertz. So you will be able to now get FM. What is FC minus FM and what is FC plus FM? This I'm not calculating. So this USB, this is called LSB. LSB will be something like 9.99 megahertz, and this will be around 10.01 megahertz. Okay, if you add these two, so that is what we will get. Now the question is, what is the amplitude of the two side bands? How we will calculate the amplitude of the side bands? Let me erase this. To calculate the amplitude of USB or LSB, let me write those amplitude of SB side bands. So side bands amplitude will be given by mu AC by 2. Okay, So what is here? What is the mu here? Mu is actually the depth or index, that is 0.03, sorry, 0.3, because it is 30 percentage divided by 100, that means 0.3 is the index or depth. And what is AC? AC is 40, given the amplitude of the carrier wave. Then it will be 20. So we'll get 6 volt as the amplitude of the side bands. Okay, this is how uh, you have to solve numerical problem related to this amplitude modulated signals. Okay, so we'll stop it here for today, and next day we'll learn about various kind of waves: ground waves, space waves, sky waves, etc. Okay, so bye for today.